Hi, and welcome to this section of the Algebra Word Problem Tutor. And in this section, we're going to deal with problems that involve work, okay? So everybody's heard of the concept of work. You know, you work when you wash dishes, you work when you wash the car, you work when you mow grass, and that's the concept of work. And so these problems are all going to deal with people doing work at different rates, okay? And the question will generally say, somebody can mow a grass in this amount of time, and another person can go off and mow the grass in a different amount of time. If they work together, how long will it take them to mow the grass, for instance? That's one example. So you have people doing work at different rates, at different speeds, okay? And you need to know a little bit about work in order to be able to apply that. So in order to do that, let me give you a little primer on work in general, so that when we do our problems, it won't be so foreign to you. Okay. So what we're talking about here is work, okay? And, when you do work, you always have to talk about how fast does that work get done. I mean, that's something we always think about. When you wash dishes, okay, maybe it takes you 30 minutes. Maybe somebody's a little bit faster than you, maybe it'll take them 20 minutes. Maybe there's somebody that's just really slow, it takes them an hour. So the amount of time it takes you to complete a task really tells you how fast you're doing that work. And another way of saying that, which you'll see in your textbooks, is it's telling you the rate at which the work is done. So sometimes you'll see words like rate, the rate of the work done. So anytime you're talking about work, you're always going to be talking about the rate at which the work is done. Okay, so you're given a job, okay, like mowing the lawn, okay, and I mow the lawn in 6 hours. So I'm doing it at a certain rate, at a certain pace, okay? So if you know how fast the work is being done, okay, and you multiply that, that's the big X here, multiplication, times the time that you're doing the work, the time that you're working, okay, the rate at which the work is done times how long you actually do the work is going to give you the total work done. Okay, this is just a this is an equation in words here. This is just an idea we need to talk about a little bit here. If you know how fast you're doing the work, the pace at which the work is being done, and you multiply that by how long you actually do the work, then you will get the answer that you will get when you multiply these two numbers together will be the amount of work actually done over that period of time. Okay, so an example here for this part of it, which is the rate at which work can be done, an example would be, okay, so an example of this one here and this type of thing here, the rate at which the work can be done would be that you can mow 1/2 of a lawn per hour. Okay, so the rate that you do the work is always going to be doing something per some unit of time. So in this case, it's 1/2 of a lawn per hour. Or maybe if it's painting a fence, it'll be painting one fence per day. Or if it's putting shingles on a roof, you can do 1/3 of a roof per hour or something like this. So you're always going to have, when you're talking about the rate of work done, nothing too fancy. It's just talking about how much work you can do in a given amount of time. That's what the rate is. Okay, so that would be an example here in real world terms. The time working would just be, just like what we were talking about. It could be just like 2 hours, let's say. So let's say I tell somebody I can mow 1/2 of a lawn per hour. Okay, and I actually mow for 2 hours straight. If I multiply these two numbers, 1/2 times 2, then that would give me 1 lawn mowed. And that would be an example of the total work done. Okay, so I'm trying to give you some concrete examples of what this rate and this time and this total work stuff is. If I can mow 1/2 of a lawn every single hour, but I push the mower for 2 hours, then it makes sense that I'm going to actually mow 1 lawn in that period of time. Okay, so those are the basic ideas. So our first problem is going to use everything that we've talked about right here, and it goes something like this. Jane can paint a fence in 8 hours, and Jenny can paint the same fence in 6 hours. How long does it take to paint the fence if they work together? Okay, so what you have here is two people, and they have different skills. Okay, one person can paint the fence in a faster period of time than the other person. But we're not doing a race here. We actually put them together and let them both paint the fence at the same time. Okay? But because one person's better at painting than the other, it's not quite a straight calculation. Like if I had two people that could paint this fence in exactly the same amount of time by themselves, then if they work together, then they should be able to paint the fence twice as fast as if they were just doing it alone. But in this problem, because one person can paint the fence in 8 hours and the other person by themselves, and the other person can paint it in 6 hours by themselves, it's not quite so clear how long it's going to take them if they work together. So let's figure out how we would solve a problem like this. We're going to let the variable t, okay, be the total time to paint the fence. Okay, t is going to be the total time for, when they both work together. Okay, so remember, two people, if this board is the fence, two people are going and they're both painting the fence. T is going to be how long it takes them to paint the fence if they work together. Okay, so now we're going to dive into how to do this. Now, we said that Jane can paint the fence in 8 hours. Okay, so what does that actually mean? Jane can paint the fence in 8 hours. What it means is Jane can paint one, and I'm going to put the unit here, fence. Okay, she can paint one fence in an 8-hour period. Okay, this is all I'm writing is the numbers from the problem. One fence per 8 hours. Okay, one fence per 8 hours. This is what Jane can do. That's her rate. Okay, and remember we said the amount of work done is the rate times the time that she's worked. Now, if we multiply this little conversion factor that we sort of made here by t, which is the total time that we're saying that it takes them if they work together, remember the unit of t is hours. The reason I'm putting the units here is to show you that when you multiply, what you've done is you've created a conversion factor. Jane can paint one fence in 8 hours, and if you multiply by hours, hours cancels with hours, just like any fraction. X, y, let's see, 1 over xy times x, okay, just from back from your algebra, the x's can cancel because they're on the top and the bottom. This is a fraction, just like any other fraction, and units here can be canceled just like anything else. So if you have one fence per 8 hours and you multiply by the length of time that she works on the fence, hours cancel with hours, and you're left with how much of the fence Jane can paint by herself. Okay? So let me keep going. If this isn't totally clear, let me finish writing this out, and then I think it will be clear. So this entire quantity, once you multiply it out, is Jane's contribution to painting the fence. Jane's contribution to painting the fence. Okay, that's how much of the fence Jane herself can paint in the amount of time that they're working on it. Okay, I'm going to add to that how much of the fence Jenny can paint. Now, Jenny can paint one fence in 6 hours. One fence in 6 hours. Okay, and again, she works on it for the same length of time that the other person worked on it, so you're multiplying by t hours. Okay, again, hours would cancel with hours, and so this quantity here, once you actually do the multiplication, is going to be Jenny's work, Jenny's contribution. Okay, so in other words, this is the amount of work Jane has done, how much of the fence Jane has painted, and this is how much of the fence Jenny has painted when they have both worked the same number of hours on the project. Okay? Okay, now in the end, this has to equal one fence, because that's what we're doing. Now I want to spend some time talking about this, because once you understand why we're setting this problem up this way, every single problem that follows from this one will be very easy, because they all basically follow the same form. Okay, we already said that in order to calculate the work done, you have the rate of the work times the time that you do the work is going to equal the work done. Okay, and the problem tells us that you have these two people and they do they can paint the fence at different speeds. Jane can paint one fence in 8 hours, and Jenny can paint one fence in 6 hours. So to calculate how much work Jane does on the project, you just take her rate times the length of time that we don't know, by the way. We don't know how long it takes to paint. That's what we're trying to solve for. Whatever it is, we're going to call it t, and it's a variable. So Jane's rate times the length of time is Jane's contribution to the work of this project. Jen is the same story. She can paint one fence in 6 hours times however long we all work on it together is her contribution. When you add them up together, we know in the end the sum total of both of their contributions to the project means that they must paint one fence in the end. Okay, this is the work done sum total. So this is Jane's contribution to the fence project, however much she paints of the fence. This is Jen's contribution to however much she paints. And when you add them up, they must paint one fence together. That's what this equation is saying. It's an equation in work. You're writing how much work Jane contributes plus how much work Jen contributes equals the project. Now, once we understand that, the actual math is not very hard because I'm going to drop the units now. I just wrote the units to kind of show you what we were doing, but I can drop the units now. 1/8 times t is just simply t over 8. Okay, 1/6 times t is t over 6 equals 1. So you see the math is super easy. But if I had started this problem just telling you to write down t over 8 plus t over 6, you'd be like, where did all that come from? That's why we had to do this, to show you where it came from. Okay, now we need to solve this for t, but I have two fractions here, and I can't really just add them in their current form. So I need to find a common denominator here so I can actually solve this. So what I want to do is I want to transform these fractions into fractions with the same number on the bottom so that I can then add them and go on and combine those terms and solve for t. That's the only way I'm going to be able to do it. So what I'm going to do is I'm going to take t over 8 and I'm going to multiply this fraction by 3 over 3. Now let me just move on and come back and tell you why I'm doing this. And I'm going to take the fraction t over 6 and I'm going to multiply by 4 over 4. And I'm not going to touch the right-hand side. Now, what am I doing here? T over 8 is a fraction. I can multiply it by 3 over 3 because 3 over 3 is simply 1. I can multiply anything by 1. It doesn't do anything for me. It doesn't change the problem is what I'm trying to say. T over 6, I multiply by 4 over 4. The reason I do that is this. T times 3 is 3t. 8 times 3 is 24, plus t times 4 is 4t, 6 times 4 is 24, equals 1. Now you see why I did that. I did it because I want to get the same bottom number so I can add these fractions together. Okay? Because in this form, you can't do anything more with this problem. You can't solve for t, you can't add them, you can't do anything else. But you have to find that common denominator. So when you're doing that, and you can go back to your algebra to learn that, you just want to multiply top and bottom. And you want to do it so that you can get the same bottom number in one fraction as the other. Now notice I multiplied 3 over 3 here and 4 over 4 here. It's okay, you can pick any numbers you want, top and bottom, but your goal is to get the bottom number the same. And you're doing it, this is legal to do because you're basically multiplying by 1 in each case here. So, continuing on, how do we add fractions? 3t plus 4t is 7t divided by 24. Equals 1. So get 7t by himself. 7t is 24 because we just multiply both sides of this fraction by the number 24 and it cancels on the left and so we have 24 on the right. So then t is then simply going to be 24 divided by 7 and t, when you take 24 divided by 7 you get 3.4 hours. Okay? So what this problem says is we have two people that can paint a fence by themselves at different speeds. This person can do it in 8 hours and this person can do it in 6 hours. But when they work together, it only takes them 3.4 hours to do it, and that kind of makes sense because you know that the length of time it's going to take them is going to be less than the shortest time that either one individually could do. Okay? The trickiest part of the whole thing is just setting up this equation. And don't worry, I hope I've made this one clear, but for whatever reason, if it's not totally clear, we've got tons of more examples coming, and we'll get to see it done several times. Okay, the next problem goes like this. Mike can mow the grass in 12 hours and Josh can mow the grass in 6 hours. How long will it take to mow the grass if they both work together with separate lawnmowers? Same problem as before. This is really no different. It's just that we're mowing a grass instead of doing what we were doing last time. So we have two people that can do it in different times, and we need to write our equation. So don't forget from what we talked about before, the rate times the time is equal to the work done. In this case, the work done is where we're mowing grass. So we want to write an equation in terms of work. Okay. So let's talk about Mike first. He can mow a grass in 12 hours. He can mow one, and I'm going to put the units in the parentheses, one lawn in 12 hours. Okay? One lawn in 12 hours. That is the rate at which he can work. That is this. Okay? We're going to multiply this times the time, which we do not know, and I'm going to call it T, and that's hours. Okay? So that is the work done by Mike. Okay? And we're going to add that to the work done by the other person, which is Josh, and he can mow a lawn, one lawn in 6 hours. Okay? He can mow one lawn in 6 hours. And we're going to multiply this times T, which is hours. Okay? So this is exactly the same quantity. It's the work done by Josh. So in other words, this is Mike's contribution, how much of the lawn he mows, and this is how much of the lawn Josh mows. That's his contribution. So this is the work done by Mike and the work done by Josh, and we know when we add them together, it must equal one being one lawn. Okay? So notice, I'll just do a quick aside for you here just to point it out if you didn't see it last time. The reason I'm writing the units here is one lawn per hour multiplied by hours. Hours cancel with hours. This leaves you with a unit of lawns. So this is how much of a lawn Mike actually mows in this time. This hours cancels with this hours, so this is how much of a lawn, because that's the unit we have left over once we cancel this. This is how much of a lawn Josh mows. So this is how much of the lawn Mike mows, plus this is how much of the lawn Josh mows. Both of them together must equal one lawn. Okay, that's what we're doing here. So getting rid of all the units, 1/12 times T is just simply T over 12 plus 1/6T is T over 6, and that's got to equal 1. Okay, that's got to equal 1. So we have the same problem as before. We want to simplify and solve for T, but we have two fractions with different denominators. So we're going to do our little trick. We want to be able to convert this fraction so that it has a 12 in the bottom, and so that we can add them. So the way I'm going to do that is I'm going to multiply only this fraction by, what do you think we need to multiply by? It's going to be 2 over 2. And the reason we're going to do that is because on the top we'll have 2t, and the bottom we'll have 6 times 2 is 12. So we're picking a number over itself such that the bottom will give us what we want, okay, which is 12. Because once the bottom is 12, I can just simply add these. T plus 2t is 3t over 12. Denominator stays the same when you add fractions, equals 1. To get 3t by itself, multiply both sides by 12. Okay? And so 12 will cancel on the left. On the right, you'll have your 12. And then t will be 12 divided by 3. Divide both sides by 3 here. So then t will be 4 hours. Okay? So we've solved this problem. We have Mike, who can mow one lawn in 12 hours, and Josh, who can mow one lawn in 6 hours. And when they both work together, it only takes them 4 hours to mow the lawn, which kind of makes sense because 4 hours is less than the shortest time either one of them could do by themselves, which kind of makes sense because when they work together, they should be able to do it faster. Okay, the next problem is the following. One faucet can fill a bathtub in 12 minutes, and another faucet, separate faucet, can fill the same bathtub in 36 minutes. If both faucets are opened at the same time, how long will it take to fill the tub? So it's really the similar problem as before. You've got one faucet that can fill a tub in 12 minutes and another faucet that can fill the same tub in a longer period of time, 36 minutes. And if both of them are open at the same time, how long does it take to fill that bathtub? So this problem again involves work. So don't forget that the rate times the time is equal to the work done. In this case, the work is not mowing the grass or painting the fence. This is filling a bathtub. Okay? So let's write an equation in terms of work done by these two things. The first faucet, faucet A, can fill one tub. So I'm going to put, it can do one fill of a tub in 12 minutes. Okay? Times the time that we actually fill the tub, which I don't know, that's my unknown, but it's going to be in minutes. Now in this time I'm defining time t in minutes, and the reason I'm defining it in minutes because I'm dealing with minutes all throughout the problem. So t will be in minutes this time. This will be faucet A, and I'm going to add to that how much faucet B can contribute, and faucet B can do one fill in 36 minutes, and I'm going to multiply that by the same amount of time that again I do not know. Okay, this is faucet B. Okay, this is how much faucet A can fill the tub in that time and how much faucet B fills the tub, and together they must do one fill of a bathtub. So this is an equation in work. Okay, notice I wrote the units to show you yet again. One fill per 12 minutes. If you actually do this, the minutes will cancel with the minutes, and the unit of this part of things is fill. So this is how much of a fill faucet A contributes. Same thing here. When these minutes cancel, this is how much of a fill faucet B contributes. Fill plus fill, and then on the end over here, in the sum total, when I add up how much A contributes and how much B contributes, they should fill one bathtub. So it's a consistent equation. You're dealing with work, you're dealing with how many fills, how much of a tub you fill. Okay? 1/12 times T is T over 12 plus 136 times T is T over 36 is equal to 1. And we need to solve this for T, and we have the same problem. We need to get this fraction set up. But let me ask you this. What can we do to this fraction right here to make a 36 appear in the bottom so that I can add those two fractions together? If I take T over 12 and multiply 3 over 3, I think you'll find out here in the next step that's going to do the trick for us, because T times 3 is just simply 3T, and then 12 times 3 on the bottom is 36, which is what I need, T over 36 here. Okay? I need to get both numbers on the bottom the same so I have a common denominator equals 1. So now that I do that, I can add the top number. 3T plus T is 4T over 36 is equal to 1. Multiply both sides of this by 36, which will give me 4T is equal to 36. Okay? And then T will be 36 divided by 4, so then T will be 9 minutes. And notice that it has to be minutes, because I've been dealing with minutes everywhere, and you have to have the same unit of time there. So this problem is really similar to the others. It's just that we're getting some practice with writing this equation and writing it in terms of work done by one party, work done by the other party. Total amount of work done is what they must add to, and then just going through the math. Okay, this problem says that Mary can complete a project in 75 minutes. If Mary and Jennifer both work on the project, it takes them 45 minutes to accomplish together. How long should it take for Jennifer to complete the project by herself? So this problem has a similar flavor. It's asking you almost the same thing. Before, I told you the problem said how long it took to do a specific job by two different people, and then how long should it take them to work together. This one tells you how long it takes one person to do it and how long it takes both of them to do it together, and then you're supposed to find out how long it takes the other person to do it by herself. So we're doing the same thing, we're writing the same equation, we're just solving for a different quantity. So what we're going to do is we're going to let T equal the time for Jennifer to do the project by herself. Okay, that's what we're doing. So this T is a little bit different than it was in the last problem. The last problems, we defined T to be the total amount of time it took both of them to work on the project together. This one we're defining for the unknown in this problem, which is how long it takes Jennifer to do it by herself. So let's go ahead and write the same equation as we were doing before and go from there. So for Mary, who we know a little bit more about, she can do one project. Okay, she can do one project in 75 minutes. Okay, she can do one project in 75 minutes. Okay, and we know that when they work together, it takes them 45 minutes. So this will be 45 minutes. Okay, that's how long it takes them to work together. Okay, let me finish writing the equation out, and if it's not clear, we'll go back. Okay, now the Jennifer, who we're trying to find out how long it takes her to do it by herself, she can work on one project by herself. It takes her T minutes. We don't know how long it takes Jennifer. Okay, so this T is going to show down here because basically what we're solving for is the rate for Jennifer. How long does it take her to do one project by herself? And we're going to multiply this by the same 45 minutes. Okay, and then in the end it's going to equal one project, which is what we've always been doing. It always equals 1. So notice this equation looks the same, it's just that some of the terms are in different places. In the other problems, we were always asked to find out how long it took them to work together. Okay, so the time here and the time here was the variable. In this one, we're not asked to find that. We know how long it takes them to work together. Okay, so Mary's contribution, which is here, and Jennifer's contribution, which is here, to the project, is her contribution plus her contribution must equal one project done. And we know it takes them 45 minutes, so that goes right in there for the length of time it takes them to work on the total project together. That has to go there. But what we're effectively trying to find now is how long it takes Jennifer to work on her part if she were working by herself. This is Jennifer's rate. That's what we're trying to find. But now that we have the equation set up, the math is really not hard. 1 over 75 divided by 45 is just simply going to be 45 divided by 75. That's all that we have here. Plus, okay, 45 divided by t, 45 over t times 1, okay? And that's going to equal 1, okay? And we want to be able to solve for t, okay? So what I'm going to do is I'm going to take this 45 over 75 and I'm going to move it over here. 45 divided by t is equal to 1 minus 45 divided by 75. Take this, subtract it from both sides. So I have 1 minus that. And when you put this in your calculator, you'll find this is 1 minus 45 over 75 is 0.6. So what you'll have is 45 divided by t is equal to 1 minus 0.6, 0.4. Sometimes it's better just to go ahead and deal with decimals. In this case, it's one of those times when I felt like it was better for me to do that. Okay, so now we want to solve for t. So let's go ahead and multiply both sides by t, and that'll give us 45 equals 0.4 t. Multiply the left by t, t goes out. Multiply the right by t, and you have this. And now to find t, you just simply divide both sides by 0.4. So t, 45 divided by 0.4 is 112.5 minutes. Okay? So now we've come full circle. Okay? We know that it takes them both working together only 45 minutes to do the project. And we know that it takes one person 75 minutes to do it. Okay, and so the other person, her contribution is that her rate is she can do one project in 112.5 minutes. And in that way, when they both work together, it only takes them 45 minutes. And the final problem says, the fire department can fill a swimming pool in 120 minutes. The drain at the bottom of the swimming pool, when you open it, can drain the entire pool in 150 minutes. If the pool is filled by the fire department while the drain is actually open, then how long will it take to fill? Now let's think about this for a second. What it's saying is the fire department can fill a swimming pool 120 minutes. But once it's full, once you pull the drain, it takes longer to empty. So it takes 150 minutes to empty. So what that tells you is that even if you open the drain and fill the swimming pool with water, water's coming out of the bottom, right? But you're putting water in faster than the water's coming out. So you'll still fill it. It'll just take a long time because, you know, it tells you right here, it takes 120 minutes to fill it. It takes 150 minutes to drain it, okay? So it's definitely filling faster than it's draining. So what we're going to do is we're going to use the same kind of work equation, and you'll see the little trick here that you have to do whenever you have something draining out. It's really not a big deal at all. What we're going to do is we're going to say the fill time is just going to be equal to t. This is how long it's going to take to fill the pool, you know, when we're doing it like this, when the drain is open. Now, you can fill one pool, okay, in 120 minutes, okay? This is the conversion factor. This is the rate that you can fill the pool, okay? And you're going to multiply this by t minutes, okay? This is the rate times the time, and what this is the work to fill. This is the work contribution to fill the pool, okay? Now, I'm not going to actually put anything here yet. I'm not going to put a plus or a minus, but let me write this. When you drain it, you can drain one pool, and it takes 150 minutes, okay? And I'm going to multiply this by the same time because, again, we're filling it while we're draining it, and it takes a certain amount of time to fill, so it's going to be the same amount of time here. And this quantity is the work to drain the pool. Okay, so what this is saying is, and this is the same rate times time, it's just different rates here. This is the contribution to the water hose going into the pool. This is how much of the pool I'm filling by putting the hose in here. This is how much of the pool that's just leaving and going straight out of the drain. That's the work draining. And we know that in the end, even though I'm putting water in and water is coming out, I must fill one pool in the end. So this is an equation for work just like it was before. Now let me ask you this. When two people were working together, okay, and painting the fence together, we add their works together, right? Because I'm painting the fence, he's painting the fence. Together, we help each other, so we paint the fence faster. In this case, I'm filling the pool, but I've got something working against me. I've got water coming right out of the bottom. So I may have a huge fire hose going in here, putting gallons and gallons of water in, but look at the bottom of the pool. Gallons and gallons of water are leaving the pool. Now, luckily, I'm putting water in faster than water's coming out, but still it's working against me. So how do you reflect this in this equation? Well, these two things are not going to be added together. They're going to be subtracted, okay? This is the water going into the pool. I'm losing water out of the bottom at a certain quantity of water coming out, but in the end, even though I'm filling it, even though I'm losing it, I'm still filling one pool. This is very important. If you do not have a minus sign there, the whole problem comes out wrong. Okay, that's why we have to put a minus sign there, because it's working against us. So going to the math, 1 over 120 times t is t over 120 minus 1 over 150 times t is t over 150 equals 1. And from here on out, it becomes the same kind of problem. I need to find a common denominator. But let me show you something here. If I were to take t over 120 and multiply it by 5 over 5, and if I were to take t over 150 and multiply it by 4 over 4, what would I get? I would get 5t on the top, and I would get 600 on the bottom, and I would get 4t on the top, and I would get 600 on the bottom, and so now I have my common denominator. So there's nothing magical about this. You're just trying to pick some unity fractions here so that I can get the same bottom. It doesn't matter what the bottom is. It just has to be the same. So 5t minus 4t is t, just 1t, over 600 equals 1. So then t is going to be, multiply both sides by 600, 600 minutes. And 600 minutes is 10 hours, right? Because there's 60 minutes in an hour. So that's 10 hours. So you can see it takes a whole, a long time. And forgetting about that, when you look at this, you can fill the pool in 120 minutes, okay? But because you're losing so much water out of the bottom, it actually takes you 600 minutes to fill the pool. So, so that's how you do that kind of problem. So in this section, we have done problems that deal with work, which generally tells you person A is doing work at a certain rate, working on a fence, working on a house, working on a lawn, and person B is doing work at another rate. How long would it take them if they help each other? And instead of trying to memorize tricks about how to set the equations up, just think about what you're trying to do. You're trying to write an equation in terms of the work done when you add or subtract them, depending on if they're working together or not, or against each other, and then the total work done, the goal that you're trying to find. And doing it that way and setting it up that way will give you a bulletproof way to solve problems involving work.